Hi, I'm going to be talking today about Liquavista, a technology and display that serves to be the future of both display and paper. So, looking at the display market today, there are a lot of different technologies coming out there. You see this push toward higher resolutions, refresh rates, contrast ratios, and there are things like Samsung's new quantum dot display coming out. Uh, Now, technologies like this, they're rather simple. The way that LCDs currently have a backlight is the LEDs produce a white light. It's a blue LED with a yellow phosphor coating. So with this, you just take away that yellow phosphor coating, and you put in red and green quantum dots around it. You get your RGB values, and you get in better color reproduction. So technologies like this are cropping up everywhere. You hear new acronyms every day, but fundamentally there are only two core display technologies, and that's the LCD. And now, recently, you've seen see manufacturers coming out with OLED technology, and these are both very good at what they do, which is reproducing video for essentially in-home viewing, stationary display in 2D or with glasses 3D. But they both break down in one fundamental way, and that's if you take them outside. So this display over here is actually on. It's very hard to read. You can't really make out anything on it, and that's one of the curses of LCD right now. And OLED is the same way. This is largely because of one core thing, which has to do with they are fundamentally they're emissive technologies. That means light goes out from here. And so when you get a lot of light from, say, the sun coming in, which goes all around, things are very bright, and here you get a very washed out image. And so there are solutions out there. Things have been proposed. Now this seems rather preposterous. I mean, I don't think too many people are going to go around with tents on their laptops as a solution to this. So what is the real solution? Well, the real solution is electronic paper or e-readers. So Amazon's the biggest player right now. They've got their Kindle, and I'm sure most of you have one or have handled one, and they're great. I mean, they read a lot like paper. So what's the technology behind it? It's called e-ink. And so e-ink is based on a rather simple principle where you have these charged white and black particles. The black particles are negatively charged, and the white particles are positively charged. So you apply an electric field, and they basically reflect the pattern in those electric field lines. So you see them much like in Robert Millikan's famous oil drop experiment. You see that when you apply an electromagnetic field, you will see that they'll go along that particles that are charged will go along these lines. So this uses the same principle and uses these electromagnetic fields to create a picture. And so, I mean, that all sounds very good. So you might be wondering, is this the future? And for me, the answer is a resounding no. And I mean, so let's go over basically why this is the case. So, I mean, there are good things, but there are some bad things. And so basically, the good is that it is bistable. And so bistable means that if I put an image through it, uh, in order to retain that image, I don't need to expend any energy. And so that's great. That means that you can create a static image and not be wasting any energy. Beyond that, it is low energy even when you're switching. So that's again pretty good. And also, it's fairly high resolution, as you can see in this right here. Basically, you look at the e-ink and the paper; they both look fairly similar. The LCD looks awful, but there are some negatives, which are color. So e-ink cannot, as it stands, display color. There's work to try and get it into color, but that's very fledgling. It's going very poorly. Beyond that, video is impossible because the refresh rates here are on the order of seconds. So it takes between 3 and 4 seconds to refresh the display. For video, you need at least 24 frames per second, and that's not conceivable with this. And so as you can see here, this display appears to be flexible. However, TFTs, which form the backplane of these displays, are not flexible. So you would not be able to actually use these in a flexible setting. And so that right there is the ugly part of this. So what the future really is, in my opinion, is this technology from a company called Liquavista. So Liquavista has developed a technology called electrowetting. And so this was spun off from Philips in 2006 and then sold to Samsung. And then after that, Amazon finally got it with an intent to push it toward their e-readers. So if you look here, you can see that the indoor and the outdoor comparison, the indoor looks good because it has a backlight and it's replicating the image well. But outdoors is where it really performs well because you've got all of the sunlight to work to reflect off of it. And so talking a little bit deeper into what really electrowetting is. So basically, in what we have is a water droplet on a surface that's hydrophobic. And so what it's doing right now is it's trying to minimize the contact area because it's undesirable for them to be in contact. However, when we apply a voltage, what we see is that this spreads, and it actually increases the amount of amount of area that it has under contact. And the governing principle behind that is basically, so we look at this is Young's equation. And so basically what each of these gammas are is they are basically they have to do with the surface tension. So they're the surface tension. And they happen to be, the LV is between the liquid and the vapor, SV solid and vapor, SL is the solid and liquid. And so this is how they're related. However, when you so that's basically the equation that governs figure A. But when we get into the B regime where we apply a voltage, we have to add this term to account for the electrostatic energy. And so this is actually known so this is a principle that was discovered by Lippmann. This is called Lippmann's equation. Lippmann won a Nobel Prize for this and related work. And so basically here what we see is if we increase this voltage term, since the surface tensions are material constants, what ends up happening is that we have to increase this cosine theta term to compensate, and that is where we see this overall spread. So that's the basic electrowetting principle. And so how does this translate into a display? So looking at the figure on the right, basically the we see the optical stack over here. Okay, we've got the water pixel wall and a substrate with an electrode and an insulator. So basically in equilibrium, there's a continuous film due to the fact that that's the lowest state of energy. At these typical length scales that we use in these displays, the surface tension is more than 1,000 times stronger than the force of gravity. As a result, this leads to stability in all directions. So when a voltage difference is applied, though, in B, what we see is that basically we see this electrostatic term being added to the energy, and so the stacked state that we had here is no longer energetically favorable. And so basically what ends up happening is we get this scenario in B where the balance between the electrostatic and surface tension determines how far this oil is moved. And so this concentration allows us to make our picture. So To give you a sense of what these displays are actually like, there's a little bit of a video here that I want to show you from Liquavista.
Here at a gritty industrial center in Eindhoven, the Netherlands, engineers from a Samsung research e-paper displays in readers such as the Kindle. For e-readers, it would have the advantages of color and video.
An electrowetting display actually uses a voltage to move liquids around. Basically said what we're doing, actually by applying a voltage we have a black liquid which we basically shift aside as a curtain. So basically we open a black curtain, let the light go through, and if we want to make the pixel black, the curtain closes by taking the voltage off again. We split a pixel into a red, a green, a blue, and sometimes a white pixel. And in each of these we do this curtain. In each of these we move the black liquid. Every time I actually take one of our displays outside and put the sun on it, you think, wow, this is so much better than what is out there at the moment. For instance, if you take a 9.7-inch iPad type of display, right? I mean, if you would swap an LCD for the electrowetting display, the factor of 3 improvement in optical performance give you probably about 2 times longer battery life.
So as you can see, there are lots of different advantages, especially in higher light situations when you're outside. So if we moving on, we can take a look at what sort of performance metrics there really are in play. And so if we take a look here, paper is essentially the target that we want to hit. And so it's got a black and white reflectivity of 70, which we get very close to with this number of 60 with a 3-layer electrowetting display. Color conversion is 100, which is fantastic. Contrast ratio is actually higher in an electrowetting display than typical paper. Again, we see unlimited viewing angle, and we get a major advantage, which is video. So we will be able to replicate paper seamlessly with an electrowetting display. Whereas if you look at something like a liquid crystal display that's reflective, you get only a 50 for black and white reflectivity. Color conversion is 1/3 that of electrowetting. Contrast is close, but you can't view it. You can't view it that well, and so there are issues. And then if you look here, we get a sense of what kind of colors we can reproduce. This white line that we have over here, that represents how much color can be reproduced by an electrowetting display, which is a fair bit. This little triangle in here is what you can get with a liquid crystal display. So this is already a superior technology to LCD in color replication. And so this dotted line over here that you can see, that's OLEDs, which is still a little bit more advanced, but OLEDs cannot be used outside in the dark or in these kind of situations. Now, the bigger thing that we also see is with power consumption. A Liquavista display only uses 28 milliwatts per square inch while displaying video, as compared to OLEDs, which are 240 in video, or LCDs, which are 80 in video. And so these are huge performance gains. So basically, going over some of the advantages that we get with Liquavista is so it's low cost and low energy. So that saves you some money. Then it's full color, which is great. You get video at high refresh rates, which means that you can use this for even for gaming potentially in the future. It's flexible, and it also can be used transparently, which would allow you to basically have sort of window displays that are literally windows that display. It's flexible, so it could be used like like paper. It's reflective for outdoor viewing. You've got an unlimited viewing angle, so you can see it from anywhere. So those are major advantages. However, it is initially going to be more expensive until production can really be ramped up at large scale. And it's not fully bistable, though there is work being done to make that happen. But regardless, it is still very low energy, and this is a great solution. And so basically, the existing challenges are going to be getting costs to go down. and getting production to go up. So basically, we're going to need factories for this and a streamlined process for manufacturing them. Right now, they are not too different from existing LCD manufacturing. So uh, basically, this could be done through a conversion of LCD manufacturing facilities. Beyond that, getting to the point where this is bistable will be key in making a major breakthrough and getting full market penetration. Uh, then for any kind of transparent display, figuring out how to get power for those is going to be important. But that's a bit of a minor issue. Also, right now, voltages are on the order of 20 volts DC, which is a bit high. So ideally, we'd want to see this go down, probably into the 6 to 9 volt range. Give overall better performance, but this is a big step. Initially, it was at 200 volts initially, and that was in the year 2000. Likely, this has already been resolved, just has not been announced yet. So the world seems ready for Liquavista, and I think it can enter the commercial space pretty soon. So the outlook right now, there are rumors and leaks that suggest that Amazon will use the Liquavista displays for a new Kindle e-reader called the Kindle Flame, and there are rumors that may even happen sometime in this summer or in this coming autumn. And so that would be a cool thing to see. And so beyond that, there are rumors that that they're building or have built a new facility in China to manufacture these. And beyond this, we'll probably see this moving on beyond e-readers into e-paper and transparent displays in the future. So overall, I think the outlook is pretty positive for this technology, and that summarizes my talk on this matter.